Welcome to Calculus.
We've always been good at math. How hard could calculus be?
On this episode, Stevenson will demonstrate
So we have this first derivative test, right? So how do we use it? Well, here we go. Use the first derivative test to find the local extrema and identify any absolute extrema. So here's our function f of x, this cubic function. So the first thing we want to do is find our derivative and identify any critical points. Now remember, critical points exist when the derivative equals 0 or does not exist itself. Now, when the derivative equals 0 here, I just isolated my x squared, took square root of both sides, I got plus or minus 2. On the right here, when does the derivative not exist? Well, nowhere. It's a quadratic. They exist everywhere. Remember, their domain is all real numbers. Based on this, I have two critical points. Now notice I do not have a closed interval here, so EVT does not apply. Okay, now how do we use the first derivative test? Because up to this point, everything we've done is stuff that we already do. What we're going to do is we're going to use the graph of the derivative, and then we'll be able to use the first derivative test. So let's sketch what this looks like, my derivative. I know it's a quadratic, so it's going to be concave up, and my x-intercepts are positive and negative 2. Don't get fancy with your sketch, keep it very simple. Now you're probably still wondering, Stevenson, where's the first derivative test? Here we go. The first derivative test requires understanding what happens at your critical points, which we have here, and understanding what happens at the derivative there. Does it change sign? And if so, which way? So what we're going to do is we're going to chart the sign of our derivative using the graph of the derivative, and then we'll be able to anticipate, without actually doing any calculation, what these values are in terms of maximums or minimums. So when you do a sign chart, essentially, what you're going to do is you're going to chart your critical points. Well, in this case, all we have is positive and negative 2. Now, be very careful here. This is the sign of f prime. So since this is the graph of f prime, all we're literally going to do is look, is it above or below the x-axis? So on the interval from negative infinity to negative 2, which is represented by this piece here in my sign chart, I can see my f prime is above the x-axis, so it's positive. In the interval from negative 2 to 2, I can see my graph is below the x-axis, which means my sign of this derivative is negative. And in this last interval here, from 2 to positive infinity, I can see my graph is above the x-axis, so its sign is positive. Now, how does this help us? Well, remember, what does the first derivative test tell us? So this is a critical point, because this is when the derivative is 0. Now, what happens to the left of this point? The derivative is positive. But then on the right side, the derivative is negative. So the derivative changes from positive to negative. According to the first derivative test, that means this is a local max. Here, if I go from negative to positive, at positive 2, again, that's one of my critical points, the derivative changes sign from negative to positive. So according to my first derivative test, that's a local min. I now know, without any calculations, that at negative 2, I will get my local max, and I will get my local min at 2. Now, to actually calculate what the extrema is, though, we will have to take these numbers and evaluate them into our f of x function, so I'm going to do that off to the side. Now let's actually answer the question. So according to the first derivative test, we know that f of x has an absolute maximum of 11 when x is negative 2 because the first derivative changes sign from positive to negative. We know f of x has a local minimum of negative 21 at x equals 2 because f prime changes sign from negative to positive. Lastly, the directions did ask us to identify any absolute extrema. Now, I know these have to be locals because of the first derivative test. Now, think about it. How do I know that this has to be, or there has to be no absolute extrema? Well, Remember, this is a polynomial. Its degree is odd. So that means its end behavior is opposite. So by definition, there can't be any absolute extrema because its range will be all real numbers. So we're going to say f of x has no absolute extrema because its range is all real numbers.